I would. I'm thinking about just having a final though.
That'd be great.
Would it?
Fantastic.
Would the final be cumulative, or would it be
Yeah.
what we covered?
It would be cumulative with probably a heavier weight on this last bit on the wave equation, which would be fine because, you know, how do you solve the wave equation by transform? You know, it incorporates all the ideas that we've seen in the whole class. So
Does not having a third exam make the percentages for the grade weights different?
it would, yeah, since the grade weights are factored by having 3 exams. I kind of feel like I'd like to take a vote and see who would like to have 3 exams and who would like not. Okay, I uploaded a file to the files section. We're starting something sort of completely different now. This last few bits of class are sort of completely different than the rest of class. And I have some notes written up from the past. And what I am going to do today is share my screen that has those notes and write on them. I have already posted these notes, so you can download them. You can write on them yourself. And I'll also post my version that I write on. All right, so if you want to just listen, that's fine, because, you know, I'll post everything that we're doing here. All right, I'm just arranging windows on my screen so that I can see everything I need to see. Okay, click the raise your hand button if you would like to have a third exam.
How do you do that?
Final.
Did you say instead of a final?
In addition to the final.
Oh, in addition to the final. Okay.
Yeah, so like a third exam and then a final right after that. All right. Can everybody hear me?
Yep.
Sure.
All right. So I have two. I'm counting 2 votes for a final exam, or for a third exam in addition to the final exam. I think, given the circumstances and given the pretty unanimous vote, we'll just have a final, and we'll readjust the grades percentages accordingly. Your exam 2s are graded. They are the grades are in Canvas. I did not attempt to like weight the grades the way they're going to be weighted, especially since we might have to change that anyway. So like your score on Canvas is just out of 20 points and your homeworks are just out of 10 points. That doesn't mean that the exam is only worth 2 homeworks. You know, the ratios will be adjusted with the final grades, but I wanted to get those numbers to you in the least confusing way possible. Move my microphone over here so I sound a little more normal. And I have also uploaded in each of those scores a comment with a PDF that I've marked up. So I found the grading scheme available through Canvas to be sort of clunky. I wasn't able to like just write on it. Like every mark that I made on the page, it wanted me to like type a comment associated with it, and I didn't want to do that. I just wanted to write my comments. So I just downloaded all of your PDFs, opened them up in my Pen application, saved copies of those, and then uploaded them back. So you'll have like a file accompanying your grade that should have my writing, my feedback on it. Grades were pretty good. Again, like last exam, I felt like the grades were pretty high. So that's great. I would say the biggest thing I saw quite a bit of on the exam was just forgetting to like copy things down from line to line. Like your eigenfunctions were like, x in problem 1, your eigenfunctions were like x to the 9/2 sine of n pi natural log of x. And people just forgot to write the x to the 9/2 part, or they forgot to write the natural log of x. They would just write like x or something like that. So that you got to be real careful. In addition to all the sort of moving parts that are going on in these problems, being consistent in copying things down from line to line becomes really important. Lots of opportunities to get off track if you miscopy something. That was the biggest issue I saw. Nothing else, no other like really common issues kind of come to mind. So as you're looking through your graded exams, you can keep that in mind. I know that, like I said, a lot of the scores were very high. I feel like you guys are doing a really good job on the whole. If you are concerned about your grade, with the drop date being tomorrow, feel free to reach out to me, send me an email, send me a text. We can schedule a time to talk either later this afternoon or sometime tomorrow if you're trying to decide, what your outlook is in the class. There's a couple people that might apply to, and feel free to reach out to me if that's you. All right. So with that said, let's get started. So, can everybody read this okay? Is it coming through? Is it clear enough? It's
a little light, but it's not bad.
Screen capture of a copy of a pencil and paper. I realize that might not be quite ideal. I wonder if I can adjust the contrast. Probably not. Okay, so we have spent a lot of time working on this method of transforms, and that is really the conceptual bulk of this class. All right. The idea of a transform is a pretty interesting idea, and I wanted to really kind of take the time to understand that, and I think most of you guys got that. It's wonderful. It's amazing that you can solve boundary value problems with no time derivatives. You can solve diffusion equations. You can solve wave equations. And if we had, another month, or if it were possible to kind of get through the first part of the class quicker, we can even solve problems in higher dimensions. So you can solve a problem with like 2 spatial dimensions, a vibrating drum head, using exactly the same approach. You find a spatial transform and you apply it to the problem, and you get your 3-dimensional PDE turns into a 1-dimensional ODE. Okay, it works exactly the same. It's just that the eigenfunctions have more than 1 dimension. So there's a really cool idea that we've spent a lot of time on. We're going to end with something that a lot of students find a little bit easier, maybe even a lot easier. All right, so hopefully that's some good news. Like the hardest stuff is behind us, and these last few lectures, a lot of students find pretty straightforward. It's an alternate way of studying the homogeneous wave equation. All right, so like I said last lecture, this approach only works for let me go ahead and put homogeneous wave equation, which is UTT equals UXX with some simple boundary conditions, which we'll get to, and initial conditions, right? But the key is that the governing equation is this. There is no forcing function. There is no damping term like there was on your homework. It's just this. And that's, that's not very general. I, as a mathematician in general, I like general approaches to solve problems. It's why if you've ever seen, you might have seen a bunch of YouTube videos if you were searching for YouTube videos on this topic that were talking about separation of variables. And if you did that, you might think, boy, he's never said the word separation of variables in this class. And the reason is that, in my opinion, it's not as general as the transform method. So separation of variables works for half the problems we did in this class, and then you have to kind of bolt extra things onto it to get it to work for the others. I wanted to give you a method that works for all the problems. So, why are we studying this very specific method called the method of characteristics for just this particular wave equation? It's because it really gives us a lot of insight that the transform method struggles to deliver, right? At the end of a transform problem, you have this infinite sum of terms, and it's hard to visualize what that means, right? You can sum them up on a computer and you can make pretty plots. You can even make movies if you want. But it's just really hard to look at that infinite series solution and get any kind of intuition out of it. We saw at the last lecture that this particular wave equation with no forcing function has these really interesting properties of just traveling wave solutions that move to the right and the left. And that's a pretty intuitive solution. And this method of characteristics approach really exploits that and allows us to have more intuition than transform methods. So that's why we're going to do it. It's a very special purpose method for a very specific problem, but it's worth doing. It's a nice way to kind of end the class on a lighter note. Okay, so we start by, again, looking at our wave equation. Okay, and we can have this c squared term in there, utt equals c squared uxx. That's allowed without violating this method. And we're going to do something that looks pretty innocuous. To play with this mathematically, we're going to subtract c squared uxx from both sides, all right, which brings that term over here. And then we are going to write this whole thing now as an operator acting on u. Now, every other time in this class that I've talked about operator, I have specifically had in mind a spatial operator. So if we were looking at this problem from the perspective of a transform method, we would be trying to find the transform associated with this operator right here. We would say that's the spatial operator. Okay, but mathematically, it's entirely accurate to say, well, yeah, that is a spatial operator. This is also an operator. It's a slightly different operator acting on u. And this is an entirely equivalent, valid way to think about the problem. All right. So, we're no longer really trying to isolate space and time and think about them differently like we have for much of the rest of the class. What we're doing right now is purely mathematical. We're collecting this whole thing on the left-hand side. We're writing it down as a composite spatiotemporal operator acting on u. And then we're going to do something that looks outrageous. We're going to factor this operator. And I put that in quotes because it's not really factoring, all right? It's one of those things that doesn't seem like it should work, but it does. And so you sort of get away with it without diving too much deeper. What we've basically done is express this second order operator as a sequence of first order operators. Jordan, I'm not exactly sure what you mean by that private question. So maybe talk to me after class or see if I answer it by chance. It is entirely valid to write this second order operator as a sequence of first order operators. All right. And I'll get the same thing, right? You can try this at home. You can say, all right, let me first take this operation. Let me first take a time derivative minus c times an x derivative, right? And what will that give me? That will give me du dt minus c du dx. Okay, and then let me apply the first operator to that, which will give me d squared u dt squared minus c d squared u dx dt, right? That's if I take the time derivative of this. And now if I add c times the x derivative of this, I get plus c d squared u dt dx minus c squared d squared u dx squared. Okay, and then because the mixed derivatives can be taken in any order for a sufficiently smooth function, these two terms cancel, and we get the second order operator, right? So it looks like we treated this as a product and we used a product factoring rule. That's not actually valid, right? Because it's not a product. We can't just factor it like it's a product of, d by dt minus c d by dx times d by dt plus c d by dx. But it just so happens that this does give you the same thing as the thing above. All right, that's why we put factoring in quotes. Equivalently, you can put these in either order. Like in principle, it's not obvious that these two operators would have to commute, but it turns out they do. And so either one of these is a valid way to rewrite this second order operator. Okay, so that's an interesting observation. We've got this wave equation operator, and we can, again, for lack of a better word, factor this operator in either of two ways. All right, so it seems that if this whole thing has to be 0, it's sufficient for one of two simpler things to be 0. Either this is 0 or this is 0. All right? Because if this thing is 0, if this first order operator acting on u is 0, then when this second first order operator acts on 0, it will give you 0. Similarly, if d by dt plus c d by dx of u equals 0, then this second operator acting on 0 will give you 0. All right? So either one of these equaling 0 will satisfy the wave equation. Okay? So that's actually a pretty strong statement. We've taken a second order partial differential equation and turned it into either one of these first order ordinary differential equations. Okay, so here is that first order differential equation. Here's a second one. Either one of these can be true, and the result will satisfy the wave equation. All right, now these first order equations that result from factoring the second order wave equation have a variety of names. Okay, sometimes they're just called first order wave equations. Sometimes they're called advection equations. And my favorite name is that a lot of people just refer to them colloquially as the baby wave equations. All right, so that's kind of a fun name. All right, and so in order to, if we want to solve the full wave equation, it is sufficient to solve either one of the baby wave equations. And that's what this sort of factoring has accomplished for us. We've said, okay, got this equation, rewrite it as an operator. Hey, I can do this weird thing to the operator. This one weird trick, right? If you use this one weird trick, this is like the only time I've ever found a way to validly use that statement, like without irony. This one weird trick allows you to solve either one of two much simpler equations instead of solving the full equation. So let's think about how to solve those baby wave equations. Okay, and for no particular reason, I've chosen the second one, the one with a plus sign. All right, and there's a sort of second trick we can play to really make the behavior of this equation clear. All right, and the way it works is you say, okay, I've already seen that the full wave equation admits solutions either moving to the left or to the right. I saw that when I did transform solutions. So let's imagine that I'm thinking about the behavior of u of x and t from the perspective of a moving observer. Okay. And I imagine myself, moving with the wave in the same direction that the wave is moving. So here's the idea. At one point in time, I am at a particular position in space, and I have a value of my solution at that particular value of time and space, which could be u of x1 t1, or sorry, u of x of t1 comma t1. This is the whole solution, u of x of t1. And at some other time t2, my solution looks different. It's u of x and t2. But I imagine that I have moved, okay? And so now if I look at my solution up above me, I would have u of x of t2 comma t2. And what's happened in between those two times is that as the solution has evolved, I have moved. All right. So this is what we're going to imagine. We're going to imagine that x is some function of time. Okay. We're now going to sort of make a what's called a change of variables. But physically, what we're changing is like a different reference frame. I'm going to recast the equation not as it is viewed by a static observer, but by how it is viewed by a moving observer. And so I have a change of variables. What happens to that time derivative if x is a function of time? Okay, that is, if I am moving, if my observer is moving, then what happens to that du dt? Okay, well, actually, this is a slightly different question. All I'm asking is like, what do I observe? What change do I observe as I am moving? Like, what is the absolute rate of change of u if x is now also a function of time? Right? That's right. So I am my little moving observer, and I'm basically asking, how is my value changing? U of x of t comma t. I am my observer, and I have my value of the function, and all I'm asking is to say, well, how is this changing? All right, and I can calculate that using the chain rule, right? Here I have a function u that depends on two variables, but one of the variables x depends on the other, and so I can turn this full derivative into a product of partial derivatives using the chain rule. I get the partial of u with respect to its first argument x times the derivative of that first argument x with respect to t, plus the partial of u with respect to its second argument 2, and then you could say in principle times the derivative of that second argument with respect to t. Okay, but that's just 1. Okay, so this is the rate of change of my little value as I move along. And that looks an awful lot like the advection equation I'm trying to solve, right? So this is one thing, the rate of change of my little value as say I'm on a moving train, right? And I'm looking out the window and there's like a train next to me, and I'm looking at and seeing how my scenery changes. All right. That's what this gives. That looks an awful lot like the solution to the advection equation. Looks an awful lot like the advection equation. So the idea here is basically that, well, here I've got this thing in both of my equations. And this looks very similar, except that here I have a c and here I have a dx dt. Okay, so evidently we can make the following argument. If dx dt, the rate of motion of the observer, happens to equal c in the advection equation, then these two things are equal. And since the advection equation has this sum of partial derivatives equals 0, it must be true that if the observer is moving with speed c, then du dt equals 0. That is, if the observer is moving with speed c, the observer does not see any change in the solution at all, ever. All right. So these two statements together mean that as time evolves, no matter where my observer is in the initial value, that initial value just moves along in time with speed c. And we can, I'll come back to that. Oh, I thought I had a picture sooner. Let's not come back to that. Sorry, I know you guys don't like it when faculty scroll through their notes like this. All right. So let's write this out. Let's find a way to write this out mathematically. Okay. What I have now is basically two ODEs. The first ODE was this expectation or requirement that dx dt equals c. Okay, that's the if. If this is true. And the second is the then this is also true. So let's come up with a solution that solves both of those ODEs at the same time. They're both first order ODEs, so we need an initial condition. The initial condition for this will just be the initial value of x. X at time t equals 0 is wherever I started. We'll just call that x naught. And the initial condition for this equation here is u at time t equals 0 is going to be, well, it depends on where I started. So here's my t equals 0. Here's my x at time t equals 0. Okay. X of time t equals 0 is what we're calling x naught from up here. Okay. And I'm going to call this thing right here u at any given value of x naught time t equals 0. I'm going to call that I of x naught. Okay. So I is the initial shape of the string, right? Before we get started. So I'm now ready to solve these two equations. This is just, these are both very, very simple equations. They're not even really differential equations. You just integrate each one of them. So dx dt equals a constant. I integrate ct plus a is my value of x. I solve that initial condition. X of 0 is a, which has to be x naught. Okay, and so x is called, the value of x is x naught plus ct. And then down here, this is even simpler. Du dt is 0, so u is just some constant. That constant can depend on the parameter x naught, which appears in the initial condition. And what is that constant? Well, it has to be I of x naught. All right, when I plug in t equals 0. So x naught, we can solve for x naught in terms of x and time. We get that. And so I've just solved, by solving both of these ODEs, I have found a solution for my partial differential equation. All right. U, the solution to the advection equation, is just I of x naught, but x naught equals x minus ct. And so I get my solution, I of x minus ct. We talked about solutions of this structure last class. Remember, I is the initial shape of the wave. When t equals 0, this is just I of x. So it self-evidently satisfies the initial condition that u of x comma 0 equals I of x. So it definitely satisfies that. But what happens to that solution as time begins to increase? When we have this very specific structure that u simply depends on the difference, x minus ct. Okay, what is this saying? All right, the first result, that x is x naught plus ct, describes a family of curves that depend on your initial position. So whatever your initial position x naught is, this says that you will be moving in such a way that you're increasing in time with speed c. Along those curves, which are called characteristics, the PDE satisfies du dt equals 0. So what we've done here by splitting the problem in this way is, or not necessarily splitting, but by setting up the problem in this way, we found a family of characteristic curves along which the PDE is constant. More generally, the PDE reduces to an ODE, which happens to have a 0 right-hand side in this case. All right, with constant solution. So here's an illustration. Here is our x-axis. Again, this is one of these spatiotemporal diagrams where the vertical axis is time. And suppose I start at a position x0 as some observer. My characteristic curve takes the form x equals x0 plus ct. I'm moving to the right with speed c. So you could say slope equals speed equals c. If I start at some other position, x1, then I will move in a similar manner. And no matter where I start, my initial value of u will just be carried with me. And so what I have going on is whatever I start with at time t equals 0, say I have a little wave with 2 bumps, then at some later time, t1, it will have moved to the right. All right, and that's it. Whatever you start with, it just moves to the right. This baby wave equation has that property. I always struggle to remember which one is which. Let me come back to this. I'll come back to which one is which in a minute. Now let's look at that other baby wave equation. It's exactly the same, except there's a minus sign instead of a plus sign. All right. And we can play exactly the same trick. We can say, imagine that I am a moving observer, moving with some speed. And if I move along a curve, x is a function of t. And if I choose my speed correctly, then the PDE reduces to an ODE, a constant ODE. And I'll get exactly the same type of solution, except that my characteristics will be moving in the other direction with speed negative c. Okay, so my characteristics will move to the left, that baby wave equation. And if I have some solution at some t equals t naught, at some later time, t equals t1, which is greater than t naught, my solution will have moved to the left. These are both valid solutions to the wave equation, which explains why we saw what we saw when we watched our last video. We saw waves moving to the left, waves moving to the right, and this is why. Okay, bring this back to the full wave equation, right? We've spent some time studying our 2 baby wave equations. We know that the full wave equation is satisfied if either one of the baby wave equations is satisfied. One of those baby wave equations gives us a wave moving to the right. And one of them, that should be a plus, moves to the left. And the way that I like to remember this, or that I try to remember, like I said, I struggle, is that if I put all of the operators on the same side of the equation, right, then it moves in the direction given by the sign here. Right, so if I've got all my u's on the left-hand side, then if I have a plus sign there, it moves to the right. If I have a minus sign there, it moves to the left. If I don't put all my u's on the same side of the equation, that's going to give me the wrong answer. So I always have to kind of stop and think about this. Put all my u's on one side. If I have a plus sign, it moves to the right. If I have a minus sign, it moves to the left. Right? So
Wait, where's the writing paper?
right here. No, sorry, other drawer. Yeah. Do you want to say hi? You want to say hi to my class?
Sure. Hi.
Oh, hello.
Hello. Writing paper in here.
Oh, it's in the other. It's in the same drawer on mom's side. There you go. Okay. If either one of these is a solution and the problem is linear, it's a linear wave equation, right? There's no multiplication of u by itself or any weird functions of u. It's just derivatives, which are linear operators. So since this is a linear equation, superposition holds, and we expect that the solution can be written. The general solution to the wave equation can be written as a superposition of something moving to the right and something moving to the left, right? Where in principle, it doesn't matter what these are. We would choose f and g to satisfy the initial conditions. And this formulation is known as, I think as we said last time, is known as D'Alembert's solution to the wave equation. If you really like the chain rule and changes of variables, I've got a page in here that gives like sort of a sneaky way to get the same result a little bit quicker. I'm not a huge fan of it because of this step right here where we define two new variables, x plus ct and x minus ct. To me, that kind of feels like you already know the answer and you're just setting up some clever, quick calculation that looks impressive, but like you wouldn't have come up with on your own. So I put that in there because it's classic. It's in all the textbooks, and you might see it elsewhere, but it's not something that means a lot to me. Give me just a second. Right. Okay. So we have this general solution to the full wave equation, something moving to the left, something moving to the right. But how do we satisfy the initial conditions of the full wave equation? Remember, the full wave equation will have, UTT equals c squared uxx. And for now, let's not worry about boundary conditions. Let's just worry about the initial conditions. U of x comma 0 will be some function of x, which I'll call I0 of x because it's a condition on the 0th derivative of u. And then we'll have a condition on the first derivative of u, which I'll call I1 of x. We looked at a lot of problems in class where I1 of x was 0 and I0 of x was some shape, but they don't necessarily have to be like that. So, okay, my full solution is something moving to the right, something moving to the left. How do I satisfy these initial conditions? Well, you can just plug in these two terms, f of x minus ct plus and g of x plus ct, and force yourself to, plug them in and satisfy the resulting equations. So we have here u of x comma 0. Well, I can set time equal to 0. That's just going to give me f of x plus g of x, okay? And that has to equal I0 of x. What is ut of x comma 0? Well, if I take the time derivative of f of x minus ct, it's going to be negative c f prime. And then if I set t equals 0, that's going to be negative c times f prime of x. Similarly, if I take the time derivative of g of x plus ct and then set t equal to 0, I'm going to get positive c g prime of x. And that's going to have to equal I1. And then I can be a little fancy. I can take this expression here. I can integrate both sides with respect to x and divide by c. And then I'll have negative f plus g is 1 over c times this integral of I1 from 0 to x. Okay, and so now I have two equations for the two unknown functions, f and g, or I guess two equations for the two unknown functions f and g, and I have right-hand sides. And so I can solve this 2x2 system. All right. And you can add the equations together to solve for one of them, and you can subtract the equations from each other to solve for the other. And now I have my values for the function f and the function g in terms of the initial conditions I0 and I1. Okay, so this will allow us to write down, if the initial conditions are simple, then this will in principle let us write down solutions in closed form. Just a single function of x plus ct and x minus ct. And that is a lot easier to work with and think about than an infinite series of eigenfunctions. Okay, that's why this method is valuable. It's also super handy for drawing pictures. And we're actually a lot of the answers to homework problems in this last unit are going to be like pictures that you draw. So I want to give you an example of that in these last few minutes. All right. Right. What am I doing here? This is just another way to write the solution. Okay. You can say that the solution is f of x minus ct plus g of x plus ct, where f and g are given in this way. But if you now plug in f of x minus ct and g of x plus ct, and you add them together, you can rewrite your solution in this form. So this is like the final form of D'Alembert's solution, where the initial conditions are satisfied. So this is D'Alembert's solution with satisfied initial conditions. All right. And so what does this say? It says I take my initial value, and in particular, let's look at this first term. Suppose I1 is 0. Suppose there's just an initial shape of the string and no initial velocity. And that means this term goes away. What's left? What does this say about our solution? It says we'll take the initial shape, that's I0, split it in half. There's your 1/2. Send one of those terms to the right, or one of those halves to the right, and one of those halves to the left. And that's exactly what we saw in that video, right? We had that video of the solution from 0 to 6, where the initial condition was a triangle from 0 to 2. And that's exactly what we saw. We saw that triangle from 0 to 2 basically turn into 2 triangles with half the height of the initial triangle, one moving to the left and one moving to the right. Now, more complicated things happened after that. We'll talk about them in subsequent lectures, but I want to connect this mathematical expression to the picture that we saw in that video. So let's do another example now. Suppose C equals 1 and I have the following initial conditions. Okay, so let me just write that out a little bit more carefully. Suppose my equation is UTT equals UXX. Again, I'm not worrying about boundary conditions. We'll get to that. Imagine that it's just an infinite domain. There's no boundaries. And then I have my initial conditions, all right? And so u of x, comma, 0, that is the initial value of u, is 0 everywhere, but it's 1 between when the absolute value of x is less than 1. Okay, so that's like a bump, a square bump from -1 to 1 that is 1 unit tall. Okay, so here's my initial displacement, and here's my initial velocity is 0. This is going to be a great example of a problem that we get a much more intuitive solution from method of characteristic than we would have from transform methods. What does our D'Alembert solution tell us to do in this case? Because I1 is 0, this term is gone. Okay, we're not worrying about that yet. all we do is we take our initial shape of the string, split it in half vertically, like make it half as tall, send one of those halves to the left and one of them to the right. We can draw that. Here's our initial problem. At time t equals 0, we have our initial condition. We imagine sort of cutting it in half vertically. And then we imagine that at this moment t equals 0, they're added together, but then they start moving one to the left and one to the right. Well, at t equals a half, what has happened? They've each moved 1/2 of a unit. So the one going to the left now goes from negative 1.5 to 1/2. Right? There's that first one. Whereas the one moving in the other direction goes from negative 1/2 to 1.5. All right. And there's still this little range from negative 1/2 to 1/2 where they overlap and they sum to 1. But by t equals 3/2, they've moved sufficiently far that they've separated. Okay, the one moving to the right now goes from 1/2 to 2.5. That one we have in green. And the one moving to the left goes from negative 2.5 to negative 1/2. And from this point onward, they'll just move in opposite directions to each other for all time. Ultimately until they hit a boundary, but we haven't talked about that yet. Think about what would be involved with an transform eigenfunction solution. We have jump discontinuities in these moving squares, right? And so if we were trying to solve this with an eigenfunction expansion, and we totally could, but our solutions would only be converging like 1/n because of the jump discontinuities. And we would have all this Gibbs phenomenon, right? These oscillating solutions resulting in Gibbs phenomenon. And we would never be able to get rid of it, no matter how many terms we kept in the eigenfunction expansion. We could keep 100 terms, 1,000 terms, and we'd always still have these overshoots and this ringing in between the jumps. And it would be kind of a mess to look at. You'd have this infinite series. What is this really doing? It would not be obvious if I asked you to solve this using transform methods. But with this method of characteristics, I know we've gone a little bit quickly through some of the analysis, but the basic idea that my initial position just is reduced to half its height, 1/2 goes left, 1/2 goes right. Like that's pretty easy to understand, and it's pretty easy to draw. You don't even need a computer to draw the solution to this equation in this scenario. We'll pick up from here next lecture. You are welcome to, I will post these modified notes. You're welcome to download, the unmarked versions and print them out or do whatever you want. We'll look at some of the more complicated cases. What happens if I have an initial velocity? What happens when I hit a boundary? And we'll work through all of those cases. But the core of the idea is right here. And so I very much encourage you to go back through these notes between now and the next lecture. You're free to log off, 11:51, but if anybody has any questions, I'm happy to stick around.
Professor, could you scroll up just a tad bit so we can see f of x minus t?
Uh-huh.
Thank you.
Right there?
Yes.